Well, since it's time, we are going to start. Hello and welcome, everyone. My name is Diana Lopez. I'm the dissemination manager of the ERN-EuroBloodNet, and this is the fourth and last session of the SYNTHEMA and ERN-EuroBloodNet educational program on artificial intelligence and its applications in hematology. This program consisted of a series of 4 webinars that were held every Friday during May, and all the presentations and recordings will be uploaded to the ERN-EuroBloodNet website and YouTube channel. So this is some housekeeping notes just for you to take into account that your microphones will remain muted during the presentations. Please note that this webinar is recorded with the goal that I already told you, that the recordings will be uploaded and shared with all the network. And you can submit your questions via the chat box at any time. And at the end of each block, the speakers will be answering them. And also, if you need to turn on the Zoom translation captions, here are some simple instructions. You need to click on the Show captions on the bottom in the Zoom toolbar at the bottom, and then click on the small narrow arrow next to the CC to turn on the translation and select the speaking language and then the translation language. Well, for today, the session is titled Opportunities of Synthetic Data Generation in Rare Hematological Diseases. And this session will be divided in 2 main blocks. The first one will be focused on sickle cell disease, and the speakers are Maria del Mar Mario Pereira from Valdebrón Research Institute and also ERN-EuroBloodNet Scientific Coordinator, and Rafaela Combati from Azienda Ospedaliera Università di Padova. And for the second block, for AML, we have Eleonora Iascone from Humanitas Research Hospital. So as I said, you can submit your questions through the chat at any time, and we will have a dedicated slot after each block for question and answers. So thank you, and I give the floor to Mar, that is the first speaker of today.
Okay, so thank you, Diana, and welcome everyone. Can you see the screen?
Yes, we see it perfect. Yes, super.
Okay. Thank you. So, as Diana introduced, this is the last webinar, and we'll focus on how to apply the developments within SYNTHEMA into a specific blood disorders use cases. So first of all, very rapidly, I would like to recap on some of the concepts that we already shared in the first webinar, but for having like the whole picture and the whole concept, why we are focusing on this or why we are working together on this, because most of our disorders are rare diseases, and we share some common challenges on rare diseases about important gaps in the diagnosis of some diseases or ultra-rare diseases, or some of their common complications. And also, most importantly, we face an important challenge about clinical trials and development of new drugs for rare diseases. Having less than 10% of patients with rare diseases with authorization for a therapeutic option, and also with an important fail of clinical trials in phase 3, around 30% for rare diseases. And this is to a good extent due to the fact that we are missing real-world evidence. And one of the problems is because we are in this rare disease ecosystem and many times lacking of high-quality data in order to better understand biomarkers, endpoints that give robust results for our investigations and clinical trials. So what we want to do, what is the opportunity of being able to generate synthetic data? First of all, what is important, as we said in webinar 1 and also webinar on data quality, is that in order to generate synthetic data, we need first very good high quality real world data, because synthetic data is based on real data. But how we can leverage the real world data, and why we want to also now make a step forward and generating synthetic data, because we can use these synthetic cohorts for a better stratification of our something that is missing in oncology, and that is really crucial in order to better understand inclusion-exclusion criteria for our clinical trials or for our investigations. So we can create longitudinal data sets, combining the data that is in the electronic health record and combining also research data from genomics or any other type of omics data, as you will see for sickle cell disease with the radiomics, in order to improve both AML and sickle cell disease, that are our use cases. For subgroups classification, we can also identify very rare patterns in our subgroups, and we can enable AI-driven phenotype matching and correlation. As we said before, we can, with this synthetic data, we can do different approaches as imputation or augmentation, and we can have data to validate some hypotheses and to identify biomarkers for robust validation of endpoints for the clinical trials. We could also use this synthetic data as external control arms for faster clinical trials phases. And this is very important because, again, we are in the rare disease field, and when we have 2, 3 different clinical trials open, it is a bit challenging how to allocate our patients for control arms. So we could use this data, this synthetic data from real world data for this external synthetic control arm. And as I told you before, for this augmentation, because there are some subpopulations or chronic complications in the case of sickle cell disease, that it occurs with very low prevalence, and we don't have enough data in order to validate our. So in general, these are some of the general objectives in which we can use the synthetic data generation. So we are here, and if you see SYNTHEMA, as we present in the first webinar, the clinical part is led by the ERN-EuroBloodNet, that this is a European reference network that is established by the European Commission and the member states. And it has the potential that all what we develop within these research projects, we have the potential to scale up the results to the whole community, and 96 hospitals that now are established in Europe in 24 countries and are recognized at the national level as experts in hematology. Within this ERN, we have also a strategy to harmonize and to improve the quality of our clinical data in both oncological and non-oncological disorders. So we can facilitate the epidemiology, we can give information to support health planning, and we can identify our patient cohorts for both to promote research, but also to promote innovative therapy in both oncological and non-oncological disorders. This is the whole ecosystem. I will not go into the details because we presented the first webinar, but in order for you all to understand why it is so important to link all these results to the ERN is because we are working in this whole ecosystem that is under the umbrella of the European Commission with the European Medicine Agency. We are implementing the quality frame of the EMA, so we can also use, because we were talking about using these results for regulatory, but we need to implement all these EMA recommendations from the very beginning if we want to use the result at the end for regulatory purposes. And then we are in several projects in which we are working for the different parts that are relevant for all this innovation and research. And one of these parts is SYNTHEMA, as promoting this development of clinical outcome research platforms, and in concrete for generating synthetic data in this case. So the two use cases are sickle cell disease, non-oncological blood disorder, inherited, chronic, and very complex disease, as you can imagine. So it's a chronic condition. So it is due to a problem in the red blood cell. We will see now. But what is important here is that we understand that is really, on top of being a rare condition, is a very highly complex condition with acute events and with chronic organ damage that affects mainly all the body. And then we have a second use case that is very different from several points of views. That is acute myeloid leukemia. That is an oncological condition in which the blood cancer starts in the immature cells in the bone marrow, and these abnormal cells grow and divide too quickly, interfering with the normal blood cell production. And then the objective is more to assess overall survival of the patients. In sickle cell disease, we identify kidney disease as our use case, and I will explain now why. So you will see that this was in the beginning. We aim to have at least 1,000 patients with sickle cell disease with a multi-layer type of data, multi-model data. And for AML, they were targeting a cohort of more than 2,500 patients with de novo diagnosis of AML. So these are the clinical partners. There are 7 in total clinical partners. The sickle cell disease is led by the Bron, the AML is led in Humanitas, and as you can see, several of the clinical partners are contributing to the 2 clinical cases. So if we go now in deep in sickle cell disease, so as I told you before, it is a genetic disorder, only one mutation. It is autosomal recessive, but with more than 1,000 already identified genetic modifiers. This only mutation, the consequence is a really complex and interconnected physiopathological pathways that from the hemolysis of the red blood cell, the sickling phenomenon, the polymerization, vasocclusion of the blood flow, the chronic endothelial dysfunction, inflammation, and all these physiopathological pathways are leading, as I told you before, to acute and chronic complications affecting almost any tissue and organ of the person. So it is high heterogeneity in terms of clinical outcomes, with this multisystemic involvement, decreased life expectancy, and low quality of life. So really it's very difficult to tackle sickle cell disease because, as you can see, you can have as many research questions as organs, tissues, outcomes in the patient. What happened is that in the last years we had several new drugs that are targeting different of these aspects, but many of them fail. And fail because normally they are not good enough showing the benefit of the different drugs. Some of them also had some problems on safety, but mainly is that this benefit is not enough demonstrated. And one of the problems, as I said in the beginning, is the lack of robust biomarkers or understanding of the subpopulations or the having robust endpoints. So, as I said, so we are lacking reliable biomarkers. We don't have prognosis markers, so we normally don't know how severe or which type of phenotype the patient may have, or when this chronic organ damage, if it is going to happen at age of 8 or age of 40. So we don't have all these biomarkers for prognosis or biomarkers to understand the response to the treatments. So, and this is another of the complexity of sickle cell disease. As you can see in the slide, the distribution of the patients is really very heterogeneous in Europe because it has an ethnic background. So it highly correlates with global population movements from countries where sickle cell disease is at high prevalence, mainly African countries and Middle East. But this is also a complication to understand sickle cell disease and to develop an AI model in sickle cell disease. This is just to show you the whole heterogeneity. But also if we see the genotypes or the vaso-occlusive crisis, this is one of the most important acute event in sickle cell disease, you can very easily see, even if you are not familiar with the disease, how the genotypes are distributed completely in a heterogeneous manner in Europe, and how also the number of crises or the uptake of the standard treatment or the regular transfusion differs from one country to another country. And this is another challenge for developing AI models. So first of all, we developed the whole infrastructure to understand all this heterogeneity and to standardize all the clinical data. And as you know, this is our RADIP registry that as of today is already deployed in 10 countries with more than 100 hospitals contributing with clinical data to the RADIP. So as of today, we have more than 6,000 patients, and we develop all the automated dashboards, public and private, to be able to understand all this variability and how we can focus on specific aspects of the disease and how we can improve the quality of our data. And all this is done fully aligned with the European Medicine Agency recommendations. And then from the RADIP, we start developing our federated platform that is called Radian, and that we initially deploy in 4 countries. But the potential of this approach is that we can easily scale up our results to other centers in Europe, all these more than 100 hospitals that are already standardizing all the clinical data aligned with RADIP. And as I showed you before, we have more than 6,000 patients already with all this data, from which more than 4,000 are sickle cell disease. And this is the whole network for red blood cell in EuroBloodNet. So you can see that we have, for the non-oncological, more than 55 hospitals in Europe. This is the potential, and now more in concrete, why we focus on kidney injury. We were working before in a previous project in other complications, vaso-occlusive crisis, acute chest syndrome, then also on kidney injury and the silent infarct that will be presented by Rafaela, the part of synthetic data. But why we choose kidney injury and not vaso-occlusive crisis or other parameters for this first model? Because kidney injury, as you can see here from our data, is a very severe complication that is not happening in all our patients. It is only happening in around 1/3 of our patients. So this is from our RADIP data. So overall, combining adult and pediatric, kidney injury is happening in around 28% of our patients. But if you go to male, 21%, female, 32%. This is already interesting to understand difference in the prevalence of kidney injury between related to sex at birth. But also it's important to understand how it differs from adult for pediatric. So if you can see also in this slide, we have in adult overall 33% of kidney injury, and we didn't have this kidney injury in our pediatric cohort, even if we need to improve all this collection of data for our cohort in RADIP. But you can already see an important difference. And then now I want to bring your attention to another parameter in this slide, that is microalbuminuria, because this is the first stage for then progression to kidney disease. So we can early diagnose through microalbuminuria that the problem on the kidney disease is starting. And then if you see there, in the case of adults, this microalbuminuria is present in 64% of our patients in adults, and is already present in 35% of our children. So even if the disease is not declared, the microalbuminuria is already present. And we focus on this because it is an important complication, as you can imagine, that we are not preventing as we should be doing probably, and we need to better understand how to better care our patients for preventing for this condition. And what are the individual characteristics of our patients in terms of genetics, genotype, and genetics modifiers, in order to stratify our patients and better understand the risk of our patients to develop a renal, a kidney disease, what is also exclusion criteria for clinical trial. So we focus for the reason in this, also because, as I told you before, we will never have good synthetic data if we don't have good real data. And vaso-occlusive crisis, as of today, the quality is not really good because there are a lot of confounders or other that I will not enter now, but a lot of other variables that are impacting on the quality of the vaso-occlusive crisis. However, kidney can be more objectively monitored through the microalbuminuria parameter. And then also as a proxy, or not a proxy, sorry, but to correlate also to the kidney disorder or the risk to develop kidney disorder in the future. So we include in our use case 1,500 sickle cell disease patients with the distribution that you can see on from France, Netherlands, Spain, and Italy, with pediatric and adult cohort. So we did some flow to ensure the quality and all the that all the parameters are available or are complete for the use case. So we need the genotype. This is one of the first steps. We already had to exclude almost 100 patients because they did not have the genotype for these patients. And then also we exclude for this use case some patients that they don't have the genetic modifier. Then we include 64 clinical variables related to kidney injury, 10 SNPs that are related to hemoglobin F, and 13 metabolites that related to different pathways, metabolic pathways, that are related in different ways to the kidney function and to the hydroxyurea treatment. And then we develop this in a federated structure, as I explained before. So these are after this was a huge work, as you may imagine, to standardize and to pull all this data, and then to prepare all the research questions, the parameters, and prepare the validation frame. So these are the first results. We have much more data, but I would like to show you here the 3 models that has been developed, and then the difference between them. And these are first results, only focusing on microalbuminuria, as I told you before. Actually, on albuminuria, that is a continuous parameter that, in principle, is not impacted by many other characteristics, let's say. So it's more objective because it's from the laboratory. But then you can see how the distribution of the synthetic data versus the real data is, in general, in the 3 validations that we did, is in general better for the second model. And then we are doing some refinement with the IT developers, no? But how only for albuminuria, how complex is to have this synthetic data? If you look into the third one, you can see that this is the probability for the patient to have the value of albuminuria below a threshold, and then it accumulates the number of patients. If you see the real data in blue and the synthetic data in orange, you can very easily see how the second model is much more good and accurate with the distribution and the probability of this parameter in our data set. However, model 1 and model 3 are not really good, let's say, reproducing all this curve in the part of the curve that is the important one, because it's where the albuminuria is increasing, and then is you can distinguish the different populations. There is one moment where all the patients are already in the same value. Then all of them, of course, are equal, but you see that they don't reach this value at the same moment, or that two models do not replicate this first part, that is the one that is important from the clinical point of view, with the same accuracy. So this is only to show you how complex is to generate these models in a complex disease like sickle cell disease. But we are improving, we are trying different models, and we are now refining the model with the feedback from the sickle cell disease experts together with the IT developers to improve this model. Also, you can see in the second plot how the synthetic data is better in the second model or even the third model, but not so much in the first model, especially for some parts of the distribution of the albuminuria. And same you can see in the histograms. So what we develop also from the sickle cell disease experts, you need to validate all this. So you need to have metrics, because we need to ensure that all the results can be applicable to our patients. And as I showed you in the beginning, and for two reasons I show you, in sickle cell disease, the patients are not the same in the different countries, and are not the same if they are pediatric or adult. So we need to develop different type of metrics in order to assess fidelity, utility of the results, the clinical validation, that is what I show you now, and also we need to develop an approach for multi-country evaluation metrics, because we would need to have two types of validation. The validation of the overall synthetic data set, but also validation for each country or for each type of population to validate if the results can be extrapolated to your specific population in your country, or in pediatrics or in adults. So this is the work that we are doing. It's not finalized, but we are now in a phase of refinement. And then with this, I will hand over to my friend Rafaela Colombati, that she will explain on a very interesting part of this project on MRIs and the synthetic generation on MRIs.
Thank you, Mar, for your part of the presentation, and thank you for leaving me the floor. I am glad to share this information regarding MRI use in sickle cell disease. Why did we focus on this? We focused on this because silent cerebral infarcts are a very common complication of sickle cell disease, affecting around between 30 and 40% of children before the age of 18. These silent infarcts, which are not lesions of overstroke, but are silent in a sense that they do not cause stroke or motor deficit, they nevertheless can have huge impact on developmental capabilities, neurocognitive function, and school achievements in children with sickle cell disease. One of the problems that we discovered in Europe is that the fact that are not expert neuroradiologists in diagnosis or in diagnosis of lesions in sickle cell disease, but also not expert across all ages, meaning that the developing brain requires certain skills to be interpreted, and also their lesions require certain skills to be interpreted, was an issue that required standardization of these lesions across Europe. So in the previous GenoMed for All project, we collected images of more than 500 patients across genotypes and across ages, and we managed to develop an algorithm for the diagnosis of silent infarcts. But what we discovered is that we do not have enough real-world data for certain categories, whether they are adults or adults who had undergone stroke, whether ischemic or hemorrhagic, or we did not have enough real-world data for children under 6. In this way, we have a lack of data to interpret and analyze the disease. So that's why this need for synthetic MRI data arise to fill the gaps in real-world data in certain categories. What did we collect? We collect the dataset had different types of MRIs, sequences, FLAIR and T1, with possible presence of white matter interintensities. The segmentation tool was the SIDA algorithm developed in the GenoMed for All project, and it was mutated by previous deep learning tools developed in multiple sclerosis. The generator tools were 3D diffusion movie-based generator, and the evaluation was performed comparing segmentation tools into real and synthetic MRIs. And the next one, please. So there was an evaluation scheme. There was a trained segmentation model into synthetic and real data, and it was tested onto synthetic real data comparing performances. There was a blinded classification on synthetic and real images to identify any discrepancies, and standard metrics computed to measure similarities between real and synthetic data. So this is an ongoing important part of the project. It's not finished yet, but we hope it will in the end allow us to develop interpretation of the effect of the disease in children below 6, as well as in adults who underwent a stroke, whether hemorrhagic or ischemic. And thank you. I'm available to answer any question.
Thank you, Rafaela. So I think Diana, that we ask now if there is.
Yeah, I was about to tell you that we don't have any questions yet on the chat. I don't know if anyone wants to unmute themselves and raise up any questions or write in on the chat, and maybe we can answer it if we have any question after Eleonora's presentation. And well, if not, we can move to Eleonora's presentation on the AML block of this section.
Thank you. So if there are no questions, I can share my screen.
Yeah.
Okay.
We see it. We see it perfect.
Okay. Perfect. Thank you. Okay. So good morning, everyone, and thank you for joining the session. My name is Eleonora Iascone, and I'm a data scientist at Humanitas Research Hospital in the AI Center. And today I will be presenting the applications of synthetic data on acute myeloid leukemia within the SYNTHEMA product. So this session covers the ML use case. We go from the clinical context to the data we work with, to how we generate and validate the distinct data produced, and what this means for the patients and also for the future of the clinical research. So let me start first with the disease itself, because to understand why synthetic data matters here, I think you first need to understand what makes AML so challenging from a clinical and also a research perspective. So acute myeloid leukemia is a rare type of blood cancer, and while in a healthy body, the bone marrow continuously produces blood cells in a regulated way. In AML, these immature myeloid cells called blasts accumulate in the bone marrow, so crowding out the normal production of healthy blood cells. So AML progresses rapidly. That means that diagnosis and treatment need to happen quickly. And this disease is predominantly a disease of older adults, median age of diagnosis of 68 years. And also outcomes are strongly age dependent. So the 5-year overall survival drops below 10% in patients over 60, with respect to 28% overall. And what makes AML particularly complex is that there is not a single disease, because current classifications define multiple molecular subtypes, each one with different prognosis and also treatment implications. So diagnosis requires an integrated workup combining blood tests, marrow biopsies, and also genetic analysis. And also this depends on age, but also fitness, comorbidities, and for now, chemotherapy remains the backbone in fit patients, while older patients increasingly receive lower intensity regimens. So this biological heterogeneity and so the rarity of specific subtypes are precisely the features that make the data sharing and also the collaborative research challenging, and where synthetic data actually can play a role. So AML research faces three interconnected data challenges. So first, AML is rare, and also when you break down into the many genetic subtypes, each individual subtype may be represented only by few patients. And this is simply not enough to draw statistically reliable conclusions or to train robust AI models. Second, the privacy barriers, because patient data in this case are sensitive and governed by strict privacy regulations like GDPR. And so data from hospitals in different countries cannot simply be pooled or shared, and each institution also operates under its own legal and also ethical framework. And also, even when the data are available and enough, it is often fragmented across different hospitals. They are collected, for instance, in different formats from different sources and standards, resulting in a high heterogeneity. So together, these three challenges create a bottleneck, because to understand rare subtypes and develop better treatments, we need data from many patients across many centers. But the nature of this disease and the regulatory landscapes make this extremely difficult. So this is where synthetic data comes in, because the core idea is to train a generative model on real patients and then share the data it produces. And this data statistically mirrors the real patients, but do not correspond to any real individual. And for AML, it opens three concrete opportunities. So the first is the privacy-preserving data sharing. So synthetic data can cross institutional and also national boundaries, and enabling the aggregation of datasets from multiple sources. and also improving also the generalizability of the research findings. Second, the rare subtype mutation. So if a specific genetic subtype has only a few real examples, we can generate additional synthetic patients with specifically that profile. So giving also models and analysis more to work with. And third, accelerating clinical research. So recent works have shown that synthetic AML cohorts can reliably reproduce, for instance, survival curves, but also molecular distributions and relationships between variables from real trial data. So enabling exploratory analysis and even the creation of synthetic control arms in clinical trials where randomization is not possible. And this last point is particularly important for patients, because it means that we may be able to test hypotheses and design also better trials faster without years of collecting new data. So let me now show what the AML dataset in SYNTHEMA actually looks like. So we work with two main types of data. The first is tabular data, so consisting in structured patient records collected at each participating clinical center. And these data include both clinical information such as demographics, laboratory, but also disease classification and stratification, treatment details, and outcomes, but also genomic data, so comprehending mutation status and cytogenetic abnormalities. So in total, this dataset covers more than 2,500 patients with AML, and consisting in 157 variables, of which 55 are required across all centers. The second type of data we're working with is the digital pathology imaging, so high-resolution scans of bone marrow samples. So we work both with histopathological slides stained with hematoxylin, eosin, and gomori, which capture the tissue architecture, and cytological slides stained with MGG, which focus on the individual cell morphology. So this imaging dataset covers 979 patients with these three staining types. And these two data types capture very different aspects of the disease. One is structural and numerical, and the other visual and also high dimensional. And each of the two types require like a completely different approach also for synthetic data generation and validation. So having described what the data looks like, I want to highlight three challenges that are intrinsic to this data, and also that directly shape the technical choices we make. So first is the multimodal complexity. So working simultaneously with tabular records and imaging data means that we cannot use a single generative model for everything, and each modality requires its own pipeline for generation and validation. Second is the biological heterogeneity, combined also with the small sample size per subtype. So, as we said before, because AML is a family of distinct genetic conditions, so rare subtypes may be represented only by a few patients. And when you train a generative model on data like this, it tends to focus on the most common profiles and ignoring the rare ones, and this phenomenon is called model collapse. The third challenge is the high dimensionality of the data and the genomic sparsity. So we track the mutation status across dozens of genes, but for any given patient, most of those genes are not mutated. And this results in a matrix that is mostly zeros, which breaks standard generative architectures and requires some custom solutions. And so these three challenges set the technical agenda for everything that follows. Because, for instance, before generation, so before any synthetic data can be generated, the real data need to be carefully prepared. So first, we did data harmonization that guaranteed that the collection across the different centers shared a common codebook through using REDCap for collection. And this ensured that a variable recorded, for instance, in one center means the same thing in another one. And so this was the first step. The second step was the variable selection, because we started with 158 variables that are this number is too high compared to the data we have. So we have to reduce them to 51, retaining only those variables with sufficient completeness and clinical relevance. And third, the missing values were handled to using different strategies according to the data type we have. So we use mice for continuous clinical measurements, and also a combination of other rule-based imputation and the KNN for the genomic and the categorical variables. Also, dates were converted to dates differences, so from the date of diagnosis to preserve the temporal structure of the clinical trajectories, but at the same time also not exposing some identifiable information. So only after all these steps, the data is ready to be used as input for the generative models. So the diagram summarizes a little bit the full pipeline we have built for AML in SYNTHEMA, but this is also applicable for SCD. So data arrives from multiple clinical centers and is preprocessed and then fed into the generative model into the. So what comes out is not directly shared, but it first goes to a structured validation process. So that evaluates both the statistical and clinical quality, but also the privacy properties. And this result is a validation report that is reviewed by a committee of clinical and technical experts. And only if the synthetic data passes the predefined thresholds, it is approved for use. Otherwise, the feedback loop sends the results back to refine the generation process. So for generating the synthetic tabular data, we test and compare 3 generative models, as also shown for SCD. So a variational autoencoder, a Bayesian network, and a CT-GAN. And each one was evaluated under 3 experimental settings. So a center-wise model trained on data from a single center. Then a centralized model trained on all variable available data pulled together. That is our upper baseline. And a federated model where training is distributed across the nodes following actually the actual center distribution. And so it simulates the real federated scenario. For imaging data, we use a dedicated generative pipelines tailored to each modality. And also the choice of comparing this resetting allows us to quantify also the cost of not being able to centralize all the data and to assess whether the federated generation can actually match the quality of the decentralized one. So let me now focus on the validation component of this pipeline. So built into the pipeline, it is mandatory validation step that runs automatically at each local clinical center. So before the synthetic data is shared or used for the downstream analysis. This validation step is performed once after training, and it is not repeated every time a user requests data, but only when a new model is trained, or for instance, when a new data becomes available or a new center joins the network. So this local validation covers 3 dimensions that we evaluate simultaneously: the statistical fidelity, the clinical utility, and the privacy. And each dimension addresses a different aspect of the data quality, and all the 3 aspects must be satisfied for the synthetic data to be considered actually of good quality and trustworthy. And as I said before, the output of this step is a per-center validation report generated automatically by the validation packages. And let me now go through all the dimensions and explain why all the three dimensions are necessary. So, statistical fidelity asks whether the synthetic data actually looks like the real data. So whether distributions, correlations, and also statistical properties are preserved. Clinical utility instead asks whether synthetic data is actually useful for downstream applications and for the same research questions that the real data would answer, and if they are capable to reproduce the same clinical outcomes and supporting the same conclusions. Finally, the privacy preservation asks whether synthetic data can protect real patients, and so if it is possible to reconstruct information about any individual from the synthetic records. So it is important to have in mind that validation is not like only a quality check at the end of the pipeline, but it is the prerequisite for any downstream use of synthetic data, because without validation, you simply cannot trust the data you have generated, and you have to build trust to make this data useful. So statistical fidelity in our case was evaluated at 3 levels for clinical data. We assess the distribution similarity variable by variable, the correlation structure, and also the overall population structure using the principal component analysis. We also applied some statistical tests such as the Kolmogorov-Smirnov, Wilcoxon, or Chi-square and Fisher for both numerical and categorical variables. While for genomic data, we used more tailored metrics. So we compared the mutation frequencies gene by gene, evaluate the pairwise associations, so including commutations and odds ratios to assess also the mutual exclusivity, and to check whether the biological relationships between mutations are well preserved within synthetic data. Okay, so here you can see some of the results we obtained with the AML dataset. So, on the left, you can see an example of the first page of the report obtained. And inside this report, we can find different plots, metrics, such as the distribution comparisons, as you can see, for both numerical and clinical variables, numerical and categorical variables, together also with the performance tests to assess the similarity between real and synthetic data sets. Also, in this case, we reported the correlation analysis through the ECMATs of real synthetic data and also their absolute difference. And as you can see that the main patterns were preserved also in synthetic data, as well for the principal component analysis that confirmed that the population of the synthetic population occupies a similar space with respect to the real one. So to make these results interpretable for both technical partners, but also for clinicians, we aggregate the individual metrics and tests to a single score that we call the clinical synthetic fidelity. It ranges from 0 to 1, meaning that a score of 0 means that the synthetic data has absolutely no resemblance to the real data, so bad performance, while a score of 1 means perfect statistical similarity. So the reason we developed this score is actually practical, because when you have multiple a lot of variables and multiple statistical tests, you need a single number that tells you whether your generation is actually working. So in this case, the score performed 94%, so tells us that synthetic data closely mirrors the real population. And the same aggregation logic applies also to genomic data, where the equivalence score is called genomic synthetic fidelity. So the challenge here is higher given the sparsity of data. It makes it harder to replicate some rare mutation patterns. But also in this case, a score of 96% tells us that not only like individual mutation frequencies are well preserved, but also the whole commutation structure and the biological relationships between the genes. So statistical fidelity, however, is not sufficient to tell you that your data is actually good, because a dataset can look statistically similar to the real one, but on the other hand, it can fail to support the same clinical conclusions. So this is why we evaluate the clinical utility separately. Or in general, clinical utility can be demonstrated through different approaches. First, the replication of the clinical studies, so meaning rerunning published analysis on the synthetic data, and then verify the consistency of the clinical endpoints, and also if the statistical significance is consistent with the original findings. Then the survival analysis, so by comparing the Kaplan-Meier curves between real and synthetic cohorts, using, for instance, the log rank test to assess whether the two groups have different survival trajectories. Third, the train on synthetic and test on real. So train predictive models exclusively on synthetic data, and then evaluate their performance on the held out dataset. And if the performance is comparable, we demonstrate that the synthetic data can be useful for downstream applications. Last one is not properly a method, but more an approach we use, so the human in the loop, meaning that the clinicians are involved in the whole process from the beginning, so defining what is good, what good looks like before the generation, and also the results downstream. So here the survival analysis results. So for the overall survival, as you can see, the Kaplan-Meier curves for real and synthetic cohorts are in close agreement, and also in this case the p-value confirms that, because it is not significant, so meaning that there is no statistical significance between the two curves, so real and synthetic one. And so it means that if researcher wants to use this synthetic data to study the overall survival, would reach probably the same conclusions as with the real ones. Then we also compare the relapse-free survival. So also in this case, the two curves show a similar overall trend, but they diverge a little bit in the early follow-up period. And this is reflected in the significant log rank test. So this tells us that this synthetic data can capture the long-term survival pattern, but not yet fully replicate the early relapse dynamics. So, okay, the third dimension is the diversity. So even synthetic data is statistically faithful and clinically useful, you have to demonstrate that these synthetic data don't expose real patients. So in SYNTHEMA, privacy is evaluated using two different groups of metrics. The distance and similarity metrics, including, for instance, a distance to close record or nearest neighbor distance ratio, that measure how close the synthetic data are to the real ones, so detecting cases where a synthetic patient is effectively copying a real individual. And then we have the attack-based matrix, like the membership inference attack, that tests whether an adversary can determine, given a synthetic record, if a specific real patient was in the training set, or the attribute disclosure metric that tests whether sensitive attributes of real patient can be inferred from the synthetic data. So here's some of the privacy results obtained from the membership inference attack on AML data using as metric, defined metric DR under the curve. In this case, our optimal threshold is 0.5, meaning that the attack performs no better than a random guessing. So that means that an adversary cannot distinguish whether a real patient will use to train the model, and this is what we want to obtain. So also a specific pipeline was designed for imaging data. So the validation pipeline for histopathological images has 4 different layers. The first one is a comprehensive statistical image level metrics, such as the diffusion distance, to assess both the similarity of the patches of the synthetic patches with the real ones, but also the heterogeneity of results, because we don't want that a model like produce every time the same patch. Second, the morphological feature extraction and comparison of the distribution. So we compare real and synthetic distribution at both a nucleus, patch, but also patient level. Third, what we have to assess is the preservation of the prognostic information contained in the real images. And we do this using Cox proportional hazard models, so to compare the performance when using clinical data alone or when adding the imaging features provided by both real and synthetic patches. So this component is particularly important because it directly assesses the clinical utility. So if the synthetic patches preserve their prognostic meaning. And the last layer is the human yield factor, so consisting in blinded classification by pathologist experts. So here's some results of the morphological feature extraction and distribution comparison at the nucleus level. So 9 features were extracted, including perimeter, centricity, solidity at the nucleus level. And then their distributions were compared between real and synthetic images using the same approach we adopted for tabular data. So resulting at the end in a clinical synthetic fidelity of 89%. So, so far what I explained was the automatic validation pipeline, so when metrics and scores and also statistical tests were run locally at each center and performed automatically. But numbers are not enough, so because a synthetic dataset can score well on every metric and at the end still fail to be clinically meaningful in ways that only, for instance, a clinical expert would recognize. So this is why a lot of clinical and technical experts is directly involved in the validation process, so what we call human in the loop, and they define what goods look like and the clinical criteria and thresholds, and they review also the validation reports that are produced by the automatic part. And so actually the automated pipeline produces the evidence, the report, and then the expert committee make the decision. So so far why validation in SYNTHEMA is so complex because we have different layers, different factors. First, that I explained before was tested at the end in a centralized setting. In SYNTHEMA, the real deployment scenario is federated, so data never leaves the clinical sites. And this introduces a constraint because validation must happen under the same conditions. So you cannot compare the synthetic data to real data you cannot access centrally. So the validation have to be performed locally where clinical data don't leave the single centers. And the difficulty is that, as we said before, statistical similarity alone is not enough, and the clinician needs to trust this data. And so we need a validation process that is both technically rigorous but also clinically grounded. So this is the challenge that the federated validation framework actually addresses. So this is a summary that shows more concretely how the federated validation workflow operates in practice. So it breaks down into two main phases. The first is the local automatic validation, explained before. So once the synthetic data are generated, it is distributed to each participating node. And each center runs locally its own validation pipeline, so producing its local report by comparing the synthetic data generated to its own real data, and then producing this local report covering fidelity, utility, and privacy. So this part doesn't require manual intervention, while the second phase is the centralized federated validation, where the local report from all the nodes are collected and aggregated. And this is where also the human in the loop review takes place, because clinicians and technical experts inspect the local results and assess whether the synthetic data actually meet the predefined clinical criteria. And if the model is not accepted, the feedback loop is triggered, and another validation process is refined. If it is accepted, the synthetic data are available for downstream use. So now that we have demonstrated that actually the synthetic data can be statistically faithful, clinically meaningful, and preserving, the question is what can we actually do with the synthetic data, for instance, for the AML case? So these are some of the concrete clinical questions that we are working to answer with the AML synthetic data in SYNTHEMA, and they all share like a common thread. So they focus on older patients and rare genetic profiles, and also on treatment decisions where the evidence is scarce and not based on rules. So synthetic data in this case can be useful, for instance, to augment the underrepresented age groups, and so allows us to study patient subgroups by age, treatment intensity, and genetic risk with a statistical power that on real datasets alone cannot reach, so with their current size. And so the validation results that I showed earlier also are the foundation that makes this clinical analysis trustworthy. So let me close with some key takeaways for this part. So first, AML can be considered as a sort of paradigmatic use case because it combines all the challenges of rare disease research, small cohorts, and sensitive multimodal data, and biological heterogeneity, together with multimodal complexity. Second, we have demonstrated that the data can be clinically valid when they are built with some clinical rigor from the start in the design of the generation pipeline and in the validation framework. Validation is not a nice to have, but actually what makes the data trustworthy and useful, and the involvement of clinical experts in this case is essential. And last, that this federated architecture means that this whole solution can be scalable, because the same pipeline can operate across many network of hospitals for also other diseases, because it is quite general, and without moving patient data. So looking ahead, the remaining open challenges are less technical but more structural, because the fields now need some regulatory frameworks that formally recognize the data as valid evidence for clinical trials, for instance. And it needs also some shared standards for the validation common thresholds and methodologies to allow to better compare the results obtained across institutions, but also across the multiple diseases. So, and at the end, it needs also like a broader process of adoption. So, synthetic data is only useful if clinicians and regulators are willing to use it. So, which requires transparency and clear governance. Okay, so that's the end for my presentation, and I'm happy to take questions if any.
Thank you, Eleonora, for this wonderful presentation. I was looking at the chat and we don't have any questions yet. I don't know if anyone wants to write down any question or to unmute her or himself. We have some minutes remaining if you want to discuss any point on Eleonora's presentation or Mar and Rafaela's. So just let us know. But well, since this is the last session of this webinar program, in the upcoming weeks, we will be uploading the recordings of all the sessions and also the material, the presentations that were presented on all the webinar sessions. So thank you everyone for participating. And oh, sorry, thank you. We have one on the chat. I will read it. And we have, thank you for making this complex issue more comprehensive for us. I would like to ask if you include the flow cytometry data because it is essential in diagnosis of AML and subtypes.
Okay. Okay. Do you hear me?
Yes, we hear you.
Okay, so first, thank you for the question. I think it's like cytometry data is a crucial component for AML diagnosis. Like actually, in this current version of the SYNTHEMA AML dataset, flow cytometry data is not yet included. But of course, if maybe in the future some other centers would join and have this type of data, I think can be quite useful to introduce them and to train actual models on this type of data.
Thank you.
Thank you, Eleonora. I don't know if you want to say something, Sul, or it's fine.
Thank you very much. Since flow cytometry data cannot be reversed and looked at after, that would be very difficult, and we have to depend on the results of the flow cytometry specialist. Thank you very much for your presentations.
Thank you. And thanks for your question. I don't know if anyone else has another question to raise up. In the chat, we don't have any other question. But well, I will leave just a few seconds just in case anyone is writing down. But well, I would like to thank you to all the speakers of today's session. Thank you, Mar, Rafa, and Eleonora for your wonderful presentations. And as I said before, they will be uploaded at the ERN-EuroBloodNet website. So you will have all the material available, also the recordings, and well, that's it. And well, since we don't have apparently any other question, we can close here. And thank you all to participate. And thank you all the speakers for your presentations.
Thank you. Thank you, Diana. No.
Thank you. Have a nice day.
Nice
Thank
day.
you.
Bye.
Bye-bye.
Bye.
Thank you. Bye.